Now we need to discuss the whole topic of diversity, which is very important in ecology but also biogeography as a critical measure of the structure of a community or province or whatever ecological entity you're looking at. And this is going to work regardless of your philosophy. So whether you favor Gleason or Clements or something else, you still have to know how many taxa you have in a given place. If you remember the ecological hierarchy, we in biogeography focus on those upper measures or upper units, the biosphere, realms, biomes, regions, provinces, which we'll get to shortly. But we also worry about communities and then the lower levels there, species, populations, individuals, mapping. The lowest one, species, populations, individuals, well, that's just counting one taxa. You specialize in one particular species, so the count is one. Not very interesting. The community, like the picture that's shown here, has multiple taxa, and you need to find some way to count them. And you could just look at that and see, well, there's a single starfish predator species up in the upper right corner. There are a bunch of little sea urchins. There are probably 2 or 3 different types of algae there that you could see just from this photograph. You could just count them, but then it's also important to get an idea of, well, there are how many starfish that you've sampled. I see 1. And there are how many sea urchins there? Well, there's a good number. And then how would you count the algae? Counts of taxa is the way we do diversity measure, and it's extremely important for many different topics. So, right off the bat, I can say that instead of using the term diversity, it's better to use the word or phrase species richness, which is sometimes denoted as S, the simple count of the number of species present at a place. There is no account for sampling size for this. It is simply counting things. And I'm going to use here just an example that I've used before for my paleontology class. This is ancient data, so the La Capilla Formation in Argentina, from that place right there in the photograph, contained Carboniferous fauna, fossils, a single paleo community. And after sitting there about an hour, I and my friend Paul collected 273 individuals, which ended up being 8 species. Okay, 8. But I could have gone there. What if I'd gone there, sat down for a minute, and quickly collected 10 fossils, n equals 10, and maybe I would get that same 8. Maybe somebody else sat there or camped overnight and they ended up collecting 1,000 things and they still got that 8. If you just count the number of species, 8 is 8 is 8. And that's okay. That's one measure of the structure of that community. We could have done it just as easily with counting the different species in this picture here. 1, 2, maybe 3, 4 for the 2 algae. But there is something to be said about the relative abundance and the sampling. So there have been a whole bunch of different diversity indices that have been created. And I'm just going to give you a couple quick examples. Again, the same things that I've done in paleontology, just for those of you that want to see a little bit of familiarity to this thing. The first is what we call Margalef diversity, and it's a way to incorporate how many things you collected or how many things you counted actually. So if I denote it as S prime up here, the mathematical formula is S minus 1, and then that is divided by the natural log of n, the total number of things, the number of individuals that are sampled. And so if we go back to that same example from the previous slide, the real data would be 8 species minus 1, again divided by the natural log of 273, the number of things I collected, and we'd get a number 1.25. if we look at the two hypothetical examples that I gave, S prime is 8 minus 1 divided by the natural log of just 10, those 10 things, we get a number of 3.04. And then finally, if we look at that third example where we camped overnight and really collected a lot, S prime is 8 minus 1 divided by the natural log of 1,000, and we get a number of 1.01. Now, the actual numbers might be confusing, but you need to consider them in relative terms. Before we used this diversity index, we said all of these three cases gave us 8 species, 8 species, 8 species. But when you consider the different level of sampling, 1,000 individuals collected versus 10 individuals collected versus the reality, 273 individuals collected, you see that if I just sat there and only collected 10 things and got that 8, it's very likely that if I did collect more, if I collected 273, or if I collected 1,000, I would get something higher. So this high number, this large number, 3.04, intimates to us that the diversity is actually higher. Here's our actual data, the 1.25, and then if we sat here and collected 1,000, we get an even lower thing. What if we sat there and collected 10,000? We'd get an even lower number. All right. Here's another one. This one's called Menhinnick's diversity. This is denoted sometimes by M, and here again you take the S, the species richness, the simple count of things, but divide it by the square root of the number of individuals. And going through the same process, you'd get the actual data gives us 0.48. The hypothetical data gives us the highest number, 2.53, and then if we actually sat and collected this large number, 1,000, we'd get this lower number. Notice again, species richness is always the same, 8, 8, 8. But if you some way divide it by the number of individuals you collect, and that's what most of these indices do, then you get this range of values to tell you that, okay, if I only collected 10 things and I already got 8 different species, the diversity is probably pretty high. Here's the reality, and then here is this. And again, remember, if I collected 10,000 and still got just the 8, that would be a lower number still. Now, you may compare Menhinnick's diversity numbers from hypotheticals, from different localities, and compare them all, but you would never compare, say, a Menhinnick diversity of 2.53 with a Margalef diversity of 3.04. You would not do that. You might calculate both for a particular project or paper, but you would only use numbers within the same diversity index to compare with each other. And comparing is the key thing. Comparative diversity. Calculate the S. Calculate some sampling things, and then you could compare 2 places, 2 people collecting, 2 types of collecting. Collecting that was done in 2020 versus collecting that was done in 1995. Collecting that Charles Darwin did in the 1800s versus the collecting somebody else did in the 2020. It's a way to look at the number of taxa in an area, but also sampling and different modes of sampling. There are other types of things to consider, and that is, all right, you've got a community, some grouping of multiple species, but is it the case where you have one particular species that is very abundant and the others not as abundant? And to go back, let's go back all the way to this here. You could say that there's 4 species here, 2 types of algae. We don't know how to count them, but then the starfish, and I've got 1, and then the sea urchins, and let's say I've got 20 here. There's something about this distribution. We have a few algae, we have one of the starfish, but we have lots of this particular species. And so that becomes an issue of what we call dominance or evenness. And so just look at these two samples. Imagine a sample where I had, here's sample A on the left. I have 10 species that have been collected when I managed to collect 100 or 1,000, individuals. And every one of those 10 species, I found exactly 100 individuals. You would then say that, wow, this community or this sample is highly even, or it has higher evenness, meaning all of the species are relatively equal. Well, we know that doesn't really happen in life. In fact, most of the time you have a situation like what's shown on the right, sample B, where again I have sampled 10 species. So the simple species richness is 10. I've also collected 1,000 things, but when I do the relative abundance of all of them, the counts, one of those species, man, there's 991 of them. And the other 9 species, I just have a single one. Just qualitatively looking at that community then, I would say this one has a higher dominance. That one species, whatever it is, dominates that community. Now, notice the difference here. Both of these, S equals 10. If all you were doing was comparing richness, you'd say there's no difference between these two. But clearly, when you consider the relative abundance, this sample, this community, A, is much more even than B, which has a higher dominance. Well, there is an index for this. There's multiple indexes for this. The Berger-Parker is the simplest one to use, and it is the number of the individuals of the most abundant taxon divided by the total number of individuals. So for the first case, every one of these has an abundance of 100. So you would say the Berger-Parker index equals 100 divided by 1,000 equals 0.1. Sample B, you have the number of individuals of the most abundant taxon is 991 divided by 1,000 equals 0.991. This one measures dominance, and so the higher the number for this index, the more dominance you could say in the community. These indexes, we're going to hit them several times from now to the end of the semester, including some more complex ones. And of course, I'll show you a program, a computer program that can quickly calculate all of these, but I wanted you to have this brief introduction to them. Now, let's look at another aspect of diversity, the whole idea of alpha, beta, and gamma diversity. Alpha is simply the count of things at a local ecosystem. In the photograph here, we're looking at the intertidal area. So the surfer is heading out to the ocean. You can see the crashing waves in the distance. The intertidal area is the area between the two tides, high tide and low tide. And then you can define the supratidal area, which would be the area above the highest high tide. And you could also define the subtidal area, which would be the area that's always below the lowest low tide. There's 3 different ecosystems right there. And somebody could come along and count the number of species in those 3 ecosystems and calculate different diversities in those areas. But there's also a different way to consider that. You need to consider the whole, which is the gamma diversity. That's the number of species in all of those ecosystems. But then there's also some weird thing that we call beta diversity, which is a measure of the diversity change between 2 different ecosystems. Now, this example I've given here is an ecosystem example, but we can do this for much bigger scale. We can do it for giant provinces, the gamma diversity of the globe. the gamma diversity of North America, and then the beta diversity between the southern high plains province and the northern high plains province. Something like that. We'll be doing that the rest of the semester. This next example is just the way this is usually mathematically expressed as a series of ones and zeros. 1 equals present, 0 equals absent. The letters there on the extreme left are the series of hypothetical species, species A, species G, species K, etc. And then if that particular species is present in any of these three environments, it's coded as 1. Now I've made a separate narrated lecture for you that's going to talk in greater detail about this example, mostly because I think you're going to need some help with the whole idea of beta diversity. So that's the next narrated lecture after we've finished this one. But we've completed diversity, diversity indexes, alpha, beta, gamma, and then before we finish our little introduction to diversity, I want you to remember that there is this latitudinal diversity gradient. We went over that in great detail, but just a few things to refresh your memory and then some new things. If it is graphed, hypothetically it would look like this, that there would be, a peak in diversity, number of taxa. Now you would know that you could plot as this y-axis. It could be simple S, counts of things, or it could be Margalef diversity, those separate values, or it could be Menhenic diversity. All of them would typically then still plot up as this nice bell curve with highest values at the equator and descending in both directions towards the pole. You could plot up beta diversity here, could do all this other stuff, but before we get to that, I want you to think about, what about variation? So sometimes people take their data and look at variation in it. So here we're looking at a plot of total gastropod or snail richness by latitude, and this is the 0 degree latitude. This would be actually towards the North Pole, and so this is mostly Atlantic data, but also a lot of Pacific data. Notice that the peak of gastropod diversity, the highest number, total richness here is, I believe, in numbers of genera, just pure numbers of genera. Peaking is still in the tropics between 10 degrees and 20 degrees north latitude, and then drops off, shows an area of stability, and then continues to drop off towards the pole. And then higher than 70 degrees latitude, there's really not much data there. Now you could change that. So in this particular diagram, we've got the same gastropod data, but they coded all of them as, oh, is this one a carnivore, meaning a snail that eats flesh? There's a lot of those. Or is it a non-carnivore, a snail that does what we're most used to? It eats algae. And here, if you look at this ratio of carnivore to non-carnivore, does it show a trend? Well, it shows a trend with a little sort of the same thing. There's peaks in the sort of tropical areas, a drop off towards the subtropics and temperate zones, but then this increase again at high latitudes. Interesting data, and something that would then become an interesting project or something to consider. You could also consider, hold on, let's get rid of that, different taxa by region. So brachyurans are a particular species of crab. There's a picture of one right here. And if you look at their diversity trends by ocean, in the Atlantic, you see a nice latitudinal diversity gradient. Highest values in the low latitudes, and then these little gray dots decrease all the way as you go up in higher latitudes. Compare this with the Pacific. where I'd say that's pretty much a stable pattern over, what, almost 50 degrees of latitude. So there's some variation that can be teased apart here by basin. Here's a different group, the Anomurans, another type of large crustacean, and again, a similar pattern. The Atlantic shows a diversity gradient. The Pacific shows a relatively flat line, but then there appears to be a drop-off over here. So I just want you to realize that you can take the simple data, the counts of things, and you can vary it by region, by any ecologic feature of a particular taxon. Instead of just plotting diversity, which I know for a fact here is just counts of species, you could do this y-axis could be any number of diversity indexes to see how they go across here, or somehow examine alpha, beta, gamma diversity across this. Just different things to consider. And again, we will be hitting these throughout the semester.